We're back and we're going to do reductions of carboxylic acid derivatives. Lithium aluminum hydride is a very versatile reducing agent. It will do, this is not a complete list, but this is a good summary here. I believe there's actually a video about lithium aluminum hydride and HCl somewhere else, but this one's got a little summary. And hydrides will both reduce to CH2s. We'll just put the new H's in red here. And the other H on the alcohols, they come from HCl in the second step, so put those in black. Amides get reduced with two new H's as well, as do esters. And these H's come with the HCl, step 2. And aldehydes and ketones back in the day. Chapter 16, we learned this. And the new H on the O from HCl. And nitriles, both these new H's from lithium aluminum hydride. Both these new H's from HCl. So let's look back at our question here. If we have anhydride, ketone, amide, ester, and we want to reduce everything except for the one that's most easily reduced on this list, the aldehyde ketone combination is fastest. All the other ones are a little slower. Clearly, how do you avoid the fastest from reacting? Well, you got to protect it first. Step 1. Our favorite protecting group for aldehydes and ketones is an acetal. Ethylene glycol is very cheap and makes a nice intramolecular acetal. So that will create this protecting group for the ketone. Without getting into detail elsewhere, the molecule didn't change. I'm just focusing on this carbon right here, and everything else stayed the same. I want to reduce all of these to alcohol. This would become methanol based on this reaction. The amide will become a CH2 based on this reaction. The ester will become a CH2OH based on this reaction. Now, this down here is this is the leaving group off of the ester. It will be an alcohol for like a nanosecond. This is an alcohol attached to an alkene. You can't even stop it. It will undergo tautomerization to an aldehyde during the reaction, and the aldehyde will be reduced according to this reaction here. It will also become, yes, an alcohol. You're saying, what happened to the double bond? Well, after the first reaction of H minus, this came off as O minus. It tautomerized to an aldehyde, and then it got reduced. So step 2 is to reduce all the other functional groups. Step 2. Wow. Step 2. Lithium, aluminum hydride. You don't have to say excess, but if you want to, it's fine. Yeah, you're going to need a lot of it. And it's always followed by HCl. So that gets you to, if I had to draw what you have now, I'm going to erase this for now. After this, this will be here, CH2, CH2O. So after steps 2 and 3, you're here. How do you get rid of the protecting group? Well, Control Z is one way, but that doesn't do it in the lab. Then step 4 is deprotection. So step 1 was protection. And step 4 is deprotection. And remembering the protection was a condensation reaction. That's why DST was a good choice. Deprotection is the opposite. It is hydrolysis. The opposite of a Dean Stark trap is to add water, isn't it? And there you have it. Yeah, that's why this was worth at least 2 points. You could argue it should be worth 3, and you'd have a good argument. I think on the fall 20 exam, this kind of question was worth 3 points. And that's a nice little mini segment. It's got a lot of good review about lithium aluminum hydride on it. There's the whole screen right there. And it's got everything. Almost. And then it got too small. All right, we'll come back after this. It looks like we have in our future a nice little mechanism with a conjugate addition involved, and then another mechanism with a conjugate addition, and then a hydrolysis. And she has a question why we have 2 products there, and we'll address that when we get back. Looking forward to it.